Hello, I'm Dio De Niz. I'm the leader of the Rapid Certifiable Trust project, and today I'm going to be presenting our results. So there is a very strong need in the DoD to have a rapid certifiable fielding, and this is kind of signaled by the multiple offices within the different services. Clearly, then this implies that we need to maximize reuse, even using open source software. And we also have the need to kind of multiply the human capability. That includes techniques like learning and autonomy. However, it is clear that this cannot be deployed out of the bat. We need to have trustworthy fielding. It means we need to have fast verification, and verification and validation has been one of the bottlenecks of this process. And this is actually critical when the systems have interactions with the physical world. These systems are known as physical systems and can have dire consequences when interacting with the physical world. And we need to check these safety critical conditions. These are in terms of physics, in terms of timing, and logic, as we will discuss further. So the project Rapid Certifiable Trust is all about fast, trustworthy validation. And the way we do it is through the automation with formal verification. But of course, formal verification is famous for not being scalable. And we need to address the complexity of the systems we use in the DoD. And actually, that is the focus of our project, right? How to make this formal verification scalable and even address adaptive behavior that includes model checking as machine learning, as we have discussed in the past. So what is our technique all about? So we call it enforcement-based verification. And the key to these techniques are to leave most of the system unverified. But in order to do this, we add some small pieces of code we call enforcers that will be watching the output of this unverified code. And actually, if they deem that the output is unsafe, it will replace it with a safe action. But as we discussed before, we need to check that this safety is verified from three different angles, right? One is the logic, that the values that are output are the correct ones, the timing that are at the right time, before, for instance, we crash into a wall, and that the physical behaviors and effects that we want are actually the ones that we can observe. On top of that, we need to make sure that the enforcers are protected, because if we have misbehavior from the unverified components, that can affect and can modify actually the code of the enforcers. So we need to have this protection. And one of the things we want to target is resilience. So we need to make the system resilient to failures, resilience to changes in the environment. So how do we do this? So let's start from the physics point of view. So from the physics, we use mathematical techniques we call Lyapunov functions to create a safety envelope. And this safety envelope will allow us to check whether misbehavior can leave the safety envelope and whether the enforcer will be able to actually correct the misbehaviors and bring it back to this safety envelope and keep it in the safety envelope. We connect all these different regions of safety regions in what we call a trajectory, a safe trajectory. And then with this, we can also verify conditions like liveness, that we can ensure that actually we make progress and we are able to finish our mission. So this is, for instance, when we observe this in an example in a drone, we can see in the slide actually a trajectory of a drone that actually is, we see a misbehavior, that is the drop in the plot that we see there, and how the enforcer is able to actually recover from that failure and return the drone to the safety envelope and kind of complete the mission. This is just the math of this behavior, but we also kind of are able to implement this, and we can observe how the same behavior can be observed in this code that is actually running and controlling this simulated drone. You will see the same trajectory we just saw a minute before, and the drop that is recovered by the enforcer, and then we continue our mission. So we have these components, as we mentioned, that are unverified. we kind of see how they are kind of sensing the environment and then issuing actuation. Clearly, actuation can be compromised by misbehaviors. Therefore, we put these enforcers. But these enforcers, is the verification enough? Can we just verify them, that's it? The problem is that if they are attacked, for instance, from a cyber attack or a misbehavior of the untrusted component, then we cannot trust the behavior of the verified component. Therefore, we need to add some protection. In this case, we can think of it as a memory protection. Therefore, for us, trusted means is both verified and protected. However, as we mentioned before, these are cyber systems that need to keep sensing the environment constantly and making corrections, for instance, to avoid a crash. And one of the problems is that if one of the unverified components is misbehaving, that can kind of delay the completion of the computation and kind of miss deadlines and even kind of get into a crash, as we have been saying before. So what can we do about that? What we do is actually add a verified layer underneath in a verified hypervisor, and we put additional what we call temporal enforcers that is watching the output. And if for some reason he cannot observe an output, then what it will do is it will issue a safe action. And this safe action, for instance, in the drone will be hover, will actually prevent one of these violation of safety conditions. In order to do this composition of these two pieces, actually we called it mixed trust task, and we develop kind of different schedulers for these two pieces and the verification, the equations to verify the timing. These hypervisor, as we alluded to, actually has been extended to go beyond only the hypervisor itself, but creating these enclaves of protection that can be embedded in device drivers in the virtual machine or even in the application. So one of the challenges we face applying this technique was the type of systems that are non-holonomic, for instance, non-holonomic vehicles that cannot switch directions instantaneously. You can think of this as the fixed-wing airplane that you are seeing here. And for those cases, we need to predict safe trajectories. So while we're doing the enforcer, we also need to do the prediction of the trajectories and enforce what we call the safety cone. And this is a balance between calculating the trajectories and enforcing. And what we did is create a new framework to kind of take advantage of both. So whenever we do not need to do enforcement, then we use the cycles to create this computation of the new trajectories going forward. And then we need to develop a new techniques to verify that, for instance, the trajectories we are able to produce are enough to be able to kind of match the consumption of the enforcement into arrival, and also that the worst case response time of the enforcer actually meet the deadlines and avoid kind of critical accidents. On top of this, we actually, as mentioned before, we target resilience. So in autonomy, it's very clear the need to kind of react and adapt to multiple failures. There is a very interesting paper from Daimler and other partners called Safety First for Automated Driving. And they present these multiple operational modes where you have full capability, but as you observe different kind of failures in sensors or degradation of the environment, then you need to be transitioning to a degraded mode of operation that actually still preserves the safety, right? So targeting these, we actually enhance our real-time mixed trust framework to add enforcers that actually do safe degradation, if you will. So for example, when we have two enforcers for collision avoidance, one based on LiDAR and another based on sensor, the LiDAR is the ideal one because it will let us detect objects with a larger distance and have a maximum speed that is larger than what the sonar is able to do. But of course, if conditions change, if the LiDAR fails, or if we have fog, then we need to switch back to the sonar. But switching back is not that easy because if we are at the maximum speed possible by the LiDAR, that is not the maximum speed that the sonar can tolerate. So we add a transitioning enforcer actually that actually breaks all the way down to the maximum speed of the sonar, right? So even though that this is a logical kind of the requirement, if you will, what we need actually is the whole framework to be able to run it and verify the timing. So therefore, we add these transitioning elements, the transitioning enforcer that will allow actually connect these two enforcers together, right? But on top of that, of course, we need to kind of connect all the different systems in the, all the different components in the system, because sometimes they need to transition and adapt to the different conditions that we have. And these system-wide modes, actually for this, we created new schedulability equations to verify that we will actually meet the timing requirements required by safety. At the same time, the other aspect that was important to us was decentralized control. And we actually, I will say, investigated this issue when we have multiple subsystems that are communicated across networks. What happens when the network fails? As you can remember, so we talk about this safety envelope and misbehaviors. And this safety envelope actually is also used in this case, but now the misbehavior includes the failures of the network. And then these conditions and these techniques allows us to verify whether even with these network failures, we are able to actually keep the system within the safety envelope. And the final topic that we want to discuss is the conflict resolution of multiple CPS enforcers. Clearly, you have multiple conditions you need to check, and you will need to add multiple enforcers. So one of the challenges we have is how do we avoid these conditions, and how do we prevent kind of unavoidable trajectories, if you will. So in this particular example that we have on the right, you can see that we have 2 points that are representing 2 drones within a virtual fence, that is this rectangular area. And we want to keep not only the virtual fence, so the drones will not leave the virtual fence, but also we want to keep a minimum distance between them. So one of the things we observe is that one technique called signal temporal logic allows us to make complex expressions of continuous signals. So for instance, in this particular case, the example that we have there is we are saying, well, if the value of the signal goes beyond 0.5, make sure that the system will return to within 0.5 in less than 1 second, and will stay there for at least 1.5 seconds, right? So these complex conditions allows us to explore how to figure out expressions of conflicts among enforcers, and also allows us to quantify for how long or for how much property can be violated, or how far are we from violating the condition, right? So this allows us then to kind of model the conditions we are going after, the distance from the 2 drones and the distance from each of the drones to the borders of the virtual fence. But beyond that, we can also, for instance, encode what we call, in this particular example, a escape trajectory. So now with this this power of expression that we have, we not only figured out how to avoid conflicts, but also how to avoid trajectories that would lead us into kind of completely breaking the enforcer conditions, right? So to conclude, let me mention this. We focus on techniques to make formal verification scalable by minimizing what is verified, enforcing safety conditions with verified enforcer. We focus on certain physical systems where we need to have the correct value at the right time with the correct physical behavior, and we need to solve conflicts between different enforcers. We mention and show how we provide protection for the verified enforcers to prevent corruption from misbehaviors of the unverified components or even cyber attacks, right? We also show how we enhance all these techniques to provide resilience to environmental changes, sensor failures, network environments. And we have been working on transitions. We are working actually on a transition to fielding Navy systems that is in progress, where we use these techniques to verify that we can preserve the safety envelope of our systems. We published 17 academic and industrial publications in multiple venues and provided 2 open source projects in the real-time mixed trust runtime and the verified hypervisor. This is our team of SEI members and collaborators. Thank you so much for your attention, and I hope that I can answer your questions.